Okay, for this last chapter of the atmosphere, chapter 8, we're going to look at problems 3, 6, 10, and 11. 4 problems this time, so still not too bad. Now, starting from problem 3, the average albedo of the Earth is 0.31. Consider the following components of the Earth's surface: oceans, rainforests, deserts. How would you expect their albedo to differ from the average? So we're just looking at this of which one of these would reflect more light, which one of these would absorb more light. The oceans, the rainforest, and the desert. And it's really more something. Oceans. So, oceans, when we consider that, are kind of a plus or minus. You might expect this to be higher than normal, but this can also, because the ocean surface is reflective, that it bounces some light back. However, oceans cover the majority of the world, and so that 0.31 is with the average taken into account. But also, since oceans contain a lot of plankton, the plankton absorb that light as energy. So we have both those parts, that the reflective water, but the absorptive plankton that give the oceans more or less the average numbers that you would expect to see. So it's going to be close to 0.31 overall. Now, rainforest, the forests tend to absorb lots of light. They absorb lots of energy. They're not really reflective. So with that in mind, you would expect these guys to have a lower albedo, a lower reflective surface than the majority of the Earth. Now, the last one, deserts, because it's largely reflective sand, reflective silica, this should expect to have a much higher albedo. Probably the only thing that is really, though, if you understand albedo at all, the only thing that is really surprising is the oceans. Just because, like, you have the plus, it's reflective water, but you also have the plankton that's absorbing the light. So that's not too bad. Now, problem 6. There's been a steady decrease in carbon-14 to carbon-12 in the atmosphere over the past decade. Explain how this might be consistent with the view that the well-documented increase in atmospheric carbon dioxide concentration is primarily due to emissions from the combustion of fossil fuels. So the idea is, like, carbon-14 is formed by light zapping nitrogen into forming a nitrogen atom, forming a carbon-14, maybe then and through what is, like, this is trying to remember how it works. If it's positron emission, through positron emission, that causes it to shift. So high energy light is coming in. So if long as the carbon ratio in the air is more or less constant, the amount of carbon-14 is more or less constant, but the amount of zapped air. So over a series of processes, this carbon-14 is converted into CO2 carbon-14. This is slowly decaying over time. But it's constantly being produced and being decayed, so it achieves essentially a steady state amount. There's a steady amount of carbon-14 in the air at any given time. But if we are producing CO2 from other sources, this is carbon-12, if the rate of CO2 production is increasing over time, the ratio of C14 to C12, this is more or less constant. But if this is increasing, we're going to see this ratio decrease over time. That's all it is. It's basically that you would expect of the amount of CO2 that comes from natural sources. Maybe I'm making up a bullshit number, just maybe 1% of the CO2 in the air is carbon-14 coming from this other source. It's much, much, much smaller, but just to say 1%. So 1 out of every 100 molecules. Well, if every year we're adding another 25 molecules that is not from natural source, so it's like now 1 out of 125 because of the original 100. And then next year it's then 1 out of 150 and 1 out of 175, and so we're just getting smaller and smaller ratios until finally we're essentially carbon-14 is dropped. Now, problem 10. Problem 10 is, most of these are thought problems, not math problems. So that's kind of nice in a way. Get us away from some of the math problems of the last chapter. Discuss the possible effects of the following greenhouse gas chemistry on greenhouse gas chemistry. A. The southern Pacific Ocean is seeded with algae. Seed with algae. Algae, micronutrients, zinc, and iron. B. CFC's thin ozone layer. C. Urban pollution increases ozone. Increases ozone layer. And D. Rice paddies grown in, they're allowed to grow in sandy soils rather than clay rich. Okay, so each of these are its own little separate problem that we need to consider. So the first one, A, algae growth, increased out the seeding with zinc and iron is going to cause algae to increase. Algae to increase. Now, the big thing is it would, if the algae is allowed to increase, would see the CO2 to drop. Now, if the rest of the environment was allowed to grow because of the increased the phytoplankton, we could see more respiration as the zooplankton grow as well. And however, in general, the more plankton would also lower the albedo. And as they decay, they could potentially increase the methane. So we could see methane go up as they die. But lower albedo, which means there's more sunlight energy in there, so which could warm some more stuff up. But you would also see a drop in the CO2. For B, when a decrease in the ozone layer, would mean more solar energy, more solar flux. We get more energy through, which is of course going to see our temp going up. And so temp's going to be going up because the more energy gets through, which would, of course, increase ice melting. Increase ice melt. And this will produce more water vapor. Water vapor goes up. Up, and which could also increase warming as well. However, more light would also zap and decay tropospheric CFCs and NOx's. So, in terms of tropospheric gases, these guys would have a reduced residence time because the stratospheric CFCs are decaying the ozone layer. So we would have a lower residence time, but would have also these other effects. So it's a very complex system. More tropospheric ozone, of course, just sees a increase in warming. And this should have a positive feedback loop. In that loop. More warming, of course, is going to help produce more smog, which is going to then help produce more ozone, which is going to help produce more warming. And so tropospheric ozone can be a little problematic. And D, our final one, what would doing it in a different soil is that the idea is that methane is produced largely in it depends on the wesoil. And so if you do it in a sandy type soil rather than a rich clay like soil, we're going to produce less methane, and thus the lower warming potential. So choosing your soil wisely for the rice paddies could help our environment. But that's kind of a little bit trickier one. Last one here. Problem 11. One climate engineering proposal for reducing the possibilities of global warming is to inject a sulfate aerosol in the stratosphere. Discuss the climatic and other atmospheric implications of this possible intervention. So, this is both positive and negative. The idea is that sulfates will produce clouds, or produce sulfate clouds. And these clouds will see the albedo goes up. Albedo increases. And so we have greater reflection, which would then see the temp go down as we have greater reflection. However, this is why environmental science is such a tricksy minx, that it's never just one variable you can directly measure that tells you, yes, this is this. You have to constantly fight with half a dozen other variables. However, these sulfates can then go on to form acid rain. It could release acid rain. And these sulfate clouds can then act as catalytic surfaces for ozone decomposition, as we learned about the Arctic ozone hole. So, for ozone decomposition. So, in the short run, they up the albedo. But in the long run, then they help destroy ozone, and that of course increases the flux. So initially lowers the flux and then increases the flux. So unless they're removed from the atmosphere, it's maybe either a wash, pun intended, or a net negative. So it's one of those things we have to consider. But that is the 4 problems I have assigned for this chapter. With that in mind, have a good day.